I have re-recorded this lecture because the sound quality was rather poor. I kept walking away from the computer, and this is a very important lecture. In fact, when we get to rigorous coupled wave analysis, method of lines, all of the information here will apply to that, and you may want to come back and review this. So I'm re-recording it with better sound quality. The previous lecture, I introduced the transfer matrix method, and we went through a bunch of stuff. We derived the algorithm, and everything seemed to make sense. And then we showed, well, this doesn't actually work, and we explained why. In this lecture, we're going to reformulate the transfer matrix method. In fact, we're not going to use transfer matrices anymore. We're going to use scattering matrices. However, we'll still call it the transfer matrix method to be consistent with how the rest of the world calls this method. So I'll introduce then the concept of a scattering matrix. And in fact, we will do our scattering matrices much differently and I think much better than the rest of the computational community. And I'll explain why when we get there. Once we have this formulation of a scattering matrix, now we can look at devices that have multiple layers and connect them together using the framework of scattering matrices. And in the end, we'll talk about calculating reflected and transmitted power from the scattering matrices, some notes on implementation, and I also want to point to some advanced concepts, advanced ways that we can use the scattering matrices to do some very useful things. And at the very end, I'll throw out some alternative to scattering matrices, and the claims are that they're faster and still offer all the benefits of the scattering matrices. I really haven't implemented too many of them, so I can only report to you what I read from the literature. Here we go. If I was going to summarize what we did in the previous lecture, here's where we are. So we started off with Maxwell's equations from lecture 2. Then for the transfer matrix method, we assumed infinite slabs in the x and y directions and having finite thicknesses in the z direction. And we showed when that happens, we can replace the any x derivative with just jkx and any y derivative in just jky. What this is really telling us is that the only thing interesting that can happen in the x and y directions is that the waves accumulate phase according to these two components of the wave vectors. So we go into Maxwell's equations, we replace those derivatives with jkx and jky, we end up with these 6 equations. Then we normalized everything. We normalized our z coordinate by essentially dividing by wavelength or by multiplying by the free space wave number. And then we also normalized our wave vector components by dividing by k0. And when we do that, we get these 6 equations that look very similar, but they're normalized. The other thing to point out on both of these sets of equations, we only have one independent variable left, that's z, so our derivative has become ordinary. At this point, we solved the third and the 6th equation for the longitudinal components, ez and hz, substituted them into the remaining 4, and we end up here. So we have 4 equations and no longitudinal components. Now, last time we took these 4 equations and we wrote one big 4x4 matrix. Instead of doing that, we're going to keep them grouped into pairs for a little bit, and we're going to form 2 matrices. So these 2 equations become this in matrix form, and the second 2 equations become what we have down here in matrix form. So stare at that for a little bit and try to understand how we got there. Now I'm going to introduce what I call the PQ form. And this PQ form arises in a lot of different methods. This will be the first time we see it here, but we'll see it again in waveguide analysis. We'll see it again in rigorous coupled wave analysis. We'll see it again in method of lines. We won't see it again when we talk about the beam propagation method, but it is possible to formulate beam propagation method with this PQ form. Perhaps I should have done that. But anyway, to simplify things a little bit, we're going to take this big square matrix here and call it P. And then we're going to take this second big square matrix that I'm circling and call that Q. Now that we have this P and Q, we can write our two matrix differential equations this way. So now we have our two matrix differential equations. They're both first order. Now what we're going to do is substitute one of them into the other and come out with what we'll call a matrix wave equation. So at the top we have our two equations from the last slide. That's two first order matrix equations, equation 1, equation 2. So the first thing I'll do is I'll take equation 1 and take the derivative with respect to z. So I take the derivative on both sides, and what I end up with is the second order derivative of the electric fields equals P times the first derivative of the H fields. This P is a constant, so it came to the outside of the derivative operator. So now we have the derivative of the H fields. Well, if we look at equation 2, we have another way of expressing the derivative of our H fields, just Q times the E fields. So in fact, we're going to replace this derivative with Q times E. When we do that, we end up now with a second order matrix differential equation only in terms of the electric fields. We're going to call PQ now omega squared. Last lecture, the previous lecture, we had just an omega, not an omega squared, because we had a first order differential equation. Now we have second order, so we're calling this omega squared, but it's just P times Q. So we have a second order matrix differential equation, and that is our wave equation. This is what describes waves. So like before, we can solve this equation. And in fact, we can go to any differential equations book. We can look at a second order differential equation of this form, and we can immediately write its solution. Now, we have a second order differential equation. There's fewer terms here. So in fact, what we end up calculating are just the modes that go in one direction. And that'll be described by e to the minus omega z. So in fact, we have to write this twice. We have to do this explicitly now to account for forward and backward. Before, in our previous lecture, we got all of the modes, forward and backward, and we had to go in and figure out which one was which. Now we don't have to do that. Our solution is only modes that travel one way, and we explicitly write them forward and backward. So no mode sorting. That's very cool. We still have this matrix exponential, an omega, this exponential of the omega matrix. So recall from lecture 4, anytime we have a function of a matrix, we can calculate the eigenvectors and eigenvalues of that matrix and write that function this way, where we have the eigenvector matrix multiplying the function operating on the eigenvalue matrix and then dividing by the eigenvector matrix. The reason that this is simple is that the eigenvalue matrix is a diagonal matrix. It just has the eigenvalues going down the diagonal. So in fact, we just apply that function to each of those diagonal elements individually. So what we get back is another square matrix, a diagonal matrix with the function performed onto just the diagonal elements. So we tie all this together, it's just as if we had performed that function on the matrix A. So we have this exponential term, so our function is an exponential. So we can calculate the eigenvectors and eigenvalues of omega and write that matrix exponential this way. So to give you an idea what e to the lambda z looks like, that's the middle term. It's a diagonal matrix. There's all zeros out here and out here, just numbers going down the diagonal. Okay, so now we write our overall solution this way. We have the electric fields, we have our forward modes, and our backward modes. Another thing that I want to point out is we had originally calculated omega squared, but here we only have an omega. So omega and omega squared have the same eigenvectors, no problem, but when we calculate the eigenvalues of omega squared, we actually get lambda squared back, but we need a lambda in here. So there's a square root operation. We'll calculate the eigenvalues. We'll take the square root of them that you see here and then do the exponential. Just wanted to point that out. So these proportionality constants, or sometimes they're called initial values, we don't know those yet. We have to calculate those. This inverse eigenvector matrix, we will know this at this point. This will be filled with numbers. So we have a big square matrix multiplying a column vector of unknowns. This just leads to another column vector of unknowns. So we'll call that C. So now we write our solution this way, and we avoid some math. We have our eigenvector matrix times the exponential of the eigenvalue matrix, but we also took the square root of the eigenvalues, multiplying these unknown coefficients of our modes. The first term is the forward wave. The second term is the backward wave. I should say waves in plural, because there's more than one mode. So something interesting happens for this case, and first we'll need to know the dispersion relation with the normalized wave vectors, and we can write that this way. And if we look at omega squared, we'll have P times Q, so P and Q. If we do a lot of math here, we multiply these matrices together, we apply this dispersion relation, it turns out omega squared just ends up being minus kz squared in the two diagonal positions. It's a diagonal matrix that we can write this way, where this bold I is the identity matrix. There's a lot of algebra here, but it has a very simple solution, and that is always the case for linear homogeneous isotropic materials. Since omega squared is a diagonal matrix, that tells us right away that the eigenvector matrix will always be the identity matrix. So in fact, we don't even need to calculate this. We'll retain W for now, but it's just the identity matrix. The eigenvalues will come out squared, so if we take the square root of these, really lambda just equals omega. So if we take the square root of our omega, we get J times Kz. So we also immediately know our eigenvalue matrix, and we can just write it as JKZ times I. One mistake a lot of folks make in the code, when they calculate the exponential of this matrix, they use the MATLAB function exp. And what that actually does is it calculates the exponential of every element in a matrix. So these two zero elements end up being ones, which is incorrect. There is another function in MATLAB, expm, M as in Michael, which is a matrix exponential, which would do this correctly. I actually recommend not using either. I recommend extracting the diagonal from the matrix, do your math in, take the square roots, take the exponentials, and then inserting that diagonal back into the square matrix. And the reason I say that is I've had troubles with the matrix exponential function in MATLAB before. In this case, I don't think it's going to give you any troubles because it's a nice, well-behaved diagonal matrix. But later on, these will no longer be such easy matrices, and I have run into troubles. So we just found the solution for the electric fields. We also need now the solution for the magnetic fields. So I'm going to write them in a very similar way. There's one difference. I'm going to stick a negative sign here. And I can do this arbitrarily because I haven't calculated C yet, or I haven't calculated V yet. And in fact, if that negative sign shouldn't be there, that will just come out in the V's and C's. But the reason I do that is I eventually want to calculate the eigenvector matrix for H, which are the V's, from the eigenvector matrix of the E fields, which is W. And so in order to relate the two, we're going to take the derivative of this, and since we have a negative sign sitting up here, that will cancel this, and we'll end up with a derivative that is all positive. This will make it much easier to compare to the electric field solution so that we can perform this calculation. So we're allowed to put the negative sign there, and we did it for convenience. So we come away with the derivative of the mode solution for the magnetic fields. Well, remember, the derivative of the magnetic fields was Q times E, and we know the solution for the electric fields. So clearly it's Q times the solution for the electric fields, and that will equal this derivative of the magnetic fields that we had up here. So now if we look at these two equations, which must be equal, we can see that V times lambda has to equal Q times W. And so if we solve this for V, we're calculating the eigenvectors of the magnetic fields in terms of the eigenvectors of the electric fields. So this equation is always valid. And in fact, when we get to higher order models like rigorous coupled wave analysis, method of lines, that same equation still holds. In fact, everything after we arrive at the PQ form is virtually identical for all these different methods. It's just a slightly different route to get to P and Q. So here we are. Here's the solution for the electric fields. We write it this way. Since W is just the identity matrix, in principle, we really wouldn't even have to write the W's there. We could just say this exponential multiplying these mode coefficients. I'm going to keep it there to be consistent with later methods, but in fact, it doesn't need to be there. Now we have also the magnetic field solution. We can bring these together into one matrix equation, and we'll put all of the unknown, or all of our fields, EX, EY, HX, and HY, into a single column vector and call it psi. And we pull them together. Here's what our solution looks like. And so the question is, does that look familiar? Yes, that looks very similar to what we had in the previous lecture. After we sorted our modes and compiled them all back into a single matrix equation. So we've ended up at the same spot, but using a different route that didn't require any mode sorting. So there's really two routes to get to where we were. If your materials are isotropic, homogeneous, it doesn't make any sense to do what we did last time. And in fact, our route to our final solution will be this bottom route. We start with Maxwell's equations, calculate PQ, and end up with our modes. The other route would be necessary if we had anisotropic materials. However, like we discussed in the previous lecture, this will require you to sort your modes, but in the end, we're going to end up with very, very similar solutions. If we do have isotropic materials, no mode sorting, and it's actually much simpler to do that. Not too big of a deal to sort, but it is an extra step that is a little bit less convenient. Now, instead of calculating transfer matrices for each layer, which we know are unstable, we're going to calculate something called a scattering matrix for a layer. And in fact, we can connect multiple layers in any way, and this is a stable way of connecting multiple layers. So we have a lot of motivations for this. It's what we call unconditionally stable. That means your numbers won't explode unless you've made a mistake in your code. The parameters of the scattering matrices have physical meaning. The S11, as we'll learn, is reflection. The S21 is transmission. In fact, all four have physical meaning. And when we measure things in the lab, there's a piece of equipment very, very common in an electromagnetics laboratory called a vector network analyzer. And it measures scattering parameters. So the numbers you're calculating from your models will correspond to what we measure in the lab. We can extract dispersion. So imagine a wave going through multiple layers. It's bouncing around between all the different layers, but there's this overall wave traveling through these layers that has slowed down in some way. And if we want to look at that, that's called dispersion. It's very memory efficient. Other techniques for solving the multi-layer problem, we have to iterate through all the layers and store parameters along the way, and then go backward through all the layers. So memory can become a problem. It's not so much for the transfer matrix method because this is so small, but when we get to larger methods that are a generalization of this, like rigorous coupled wave analysis and method of lines, it's very easy to run out of memory. We can exploit longitudinal periodicity. So if structures are repeating in the Z direction, maybe there's 5 layers that are unique, but then that set of 5 layers repeats itself. There's some neat things we can do with scattering matrices to handle that very efficiently. It's a very mature approach. and there's a huge amount of literature on it. This has arisen to be the dominant way of handling multiple layers, but I will say that there are alternatives, and the scattering matrix approach is probably the slowest. This is not going to bite us in transfer matrix method, but when we get to larger methods like rigorous coupled wave analysis and method lines, it will slow us down. So we want to look at the geometry now of a single layer. So the middle section here is our layer, and this is embedded in the middle of a huge stack of layers. The trick here is that what I've drawn on the outside is not the next layer. So this is just as if we pulled this one single layer sub I out from the stack of layers and we're looking at it all by itself. But we can potentially put something on its right, and we'll call it medium 2. This is also what we'll call an infinite half space. This goes way out to infinity. And on the other side, potentially a different material that's also an infinite half space, meaning it goes way off to infinity this direction. So we've pulled layer I out of the stack of layers and then surrounded it by two infinite mediums on either side that can be different. The reason we're doing this will become apparent in a little bit. So we want to look at the fields everywhere. Well, clearly there's mode coefficients for the material on the left, there's mode coefficients for the material on the right, and we also have mode coefficients for the material within the layer. The layer has thickness L sub I. We can in general write the fields at any point within the layer as psi sub I. The fields immediately inside layer I, but right up against the boundary, is psi sub I at 0. And the fields all the way the other side are psi sub I at k naught times L. Now the reason I'm multiplying L by k naught is because we formulated everything with a normalized z coordinate. So we're doing that to normalize our L to make sure everything works. So we have this convention for the forward waves, and we have the same convention for our backward waves. So this is how we define all of our parameters and where they exist. For a single layer with infinite materials on either side, we've pulled layer I out of the stack of layers, and it's all by itself right now. So let's look at how the fields are related. We already have an expression to write the field within this layer I. That shouldn't be any surprise. But now I've added the subscript I just to remind us this is the field in the ith layer. So we want to look at our boundary conditions now at this first interface. It's not the mode coefficients that are equal on either side, it's the fields. Remember our physical boundary conditions. The transverse component of the fields are continuous across the interface. Well, fortunately, we eliminated the longitudinal components that are discontinuous, and we're only left with the ones that are parallel to that interface, EX, EY, HX, and HY. So all of those terms are continuous across the interface. So what are the fields in medium 1 right up against this interface? Well, we just write it this way. It's the eigenvector matrix for the fields in medium 1 times the mode coefficients. Then on the second side of the interface, the fields are the psi sub I at 0. So we have the eigenvector matrix for the ith layer multiplying the mode coefficients. Now there is this exponential matrix sandwiched in here, but we made the z coordinate 0, so that exponential matrix becomes the identity matrix, and we just dropped it out. But that technically there is one in here, but if we set z equal to 0, we get the identity matrix and it's gone. Now we look at the boundary conditions for the second interface. So the fields on the left side are psi sub I at k naught L. So now we write this out, psi sub I at k naught L. And of course the fields in the second medium right against the interface are just psi sub 2, which we write as their eigenvectors in medium 2, times the mode coefficients in medium 2. So all we've done here is express the fields within the ith layer and match boundary conditions at either interface. So we have to stop with that temporarily and define what we call the scattering matrix. A scattering matrix is a matrix that really relates inputs to outputs. So we'll draw our layer as a box here. And we can have a wave coming in from the left. So it's coming in from medium 1, so we'll call that C sub 1 in the forward direction. One of two things can happen to that. It can transmit through the layer and contribute to the modes in the second layer in the forward direction. And that forward transmission is described by our S21 transmission parameter. The second thing that can happen to a wave coming in from the left is that it reflects. And that is described by S11, or our reflection parameter. And that contributes to energy or power in the modes in one that are traveling to the left. Well, we can look at it from the other direction. We can have a wave coming in from the left, and it also can either transmit, described by S12, or reflect, described by S22. So our inputs are C1 plus and C2 minus. So here are our inputs. We multiply that by the scattering matrix, and we get the outputs. C1 minus, which is what gets reflected, and C2 plus, which is what gets transmitted. So the scattering parameters have physical meaning, and this is the convention that's been used for many decades, and it is so common in electromagnetics labs. You'll hear many people just say the word S11 and not even say reflection, because it's so common. Everybody hears S11 and immediately, oh, okay, that's reflection. And the same with S21. That implies transmission. So common, people will just say S21 and not even say transmission. So that convention has been around for decades. So now that we know how our scattering matrix is defined, we can go back to the slide before that where we had two equations that enforce the boundary conditions at our two different layers. We're going to take those two equations that we derived, and we're going to solve both of them for the mode coefficients inside the layer. So C sub I. So this was the boundary condition equation for the first layer, but we solved it for the mode coefficients within the ith layer. We took our second equation that enforced boundary conditions at that second interface, and we solved for the mode coefficients in the ith layer. So now we have two equations solved for C sub I. So we can set these equal now. And so when we do that, we've eliminated the C sub I coefficients. Then we can manipulate this to get it in the form of a scattering matrix. One thing that's going to help us along the way, notice both of these have some kind of eigenvector matrix being pre-divided by, or pre-dividing a second eigenvector matrix. Here it's the eigenvector matrices for medium 1. Over here it's the eigenvector matrices for medium 2. But we see the same form. So I'll write it just in general, W sub i's, and here's J, which could be 1 or 2, depending which equation we're talking about. But in general, we can write this as just 1/2 this matrix, where the two elements along the diagonal are equal, and the two elements along this opposite diagonal are also equal. And we would write A and B this way. It takes a bit of algebra to show that, but we can use this and it will really simplify our derivation here. Anyway, so these two equations set equal, and manipulating these eigenvector matrices, we get to this. Now what I like to do is take this matrix equation, write it as two separate equations, then change the order of the terms to bring C1 minus and C2 pluses over to the left, and the C1 plus and C2 minuses over to the right. Then we can write those two equations in block matrix form, and it turns out that will be our scattering matrix. If we do this, what happens? So here's our general scattering matrix, and after we go through all that algebra, here's our A's and B's, here's the expressions that we get. And rather than keep writing exponential of minus lambda sub I k naught L, I'll just write this as x sub I. Remember, that's a diagonal matrix with the exponentials of all the eigenvalues and also k naught L running down the diagonal. But when we do that, sandwich this a layer all by itself in between two different materials, this is the scattering matrix parameters and how we would calculate them. So the subscript I is talking about which layer we're in, and then J is either a 1 or a 2, depending whether we're talking about medium 1 or medium 2. So now here's a warning if you're reading the literature in computational electromagnetics where they're dealing with scattering matrices. 99% of the time they do scattering matrices completely wrong. Mathematically, the stuff works out, they get the correct answer, but they're doing a number of things that is a little bit silly. One is they completely scramble the meanings of the individual scattering parameter terms. The most common one that I've seen is they make S22 a transmission term, which is silly. That's really should be a backward reflection term. The S12, which is usually a backward transmission term, they make the reflection term. So suddenly the scattering matrices and the computational algorithms that they're talking about are not compatible with the scattering parameters you'd measure in the lab, and it becomes very confusing to understand what they're even talking about. The other thing that's done that's very inconvenient is that we know our scattering matrices relates modes in 2 different layers, but what they'll do is they'll have the scattering matrices relate the mode coefficients inside the layer to mode coefficients on the outside of the layer. And you notice we didn't do that. We related mode coefficients on the outside of both sides of the layer. But by doing it this way, our scattering matrices are inherently asymmetric. It's very confusing, and it really doesn't answer what's happening out here. But it's immediately asymmetric, and what we're going to do next is make ours so our scattering matrices are always symmetric, and when that happens we only have to calculate 2 terms because the other 2 scattering parameters are just equal to the first 2. Here is another limitation of how we currently have our scattering matrices and how conventional scattering matrices are. So it makes sense that the scattering parameters are a function of the materials outside the layer. Of course, we have to know the materials outside to know reflections at these interfaces, to know the scattering matrices. But once we calculate that, that means that this layer sub I is always going to have medium 1 on the left and medium 2 on the right if we're going to reuse the scattering matrix we calculated. Well, let's look at an example device and the problem with that. Let's say we have a device, a whole bunch of slabs, but there's only 3 unique layers, a red, a green, and a blue layer. Well, let's look at this green layer. We have a green layer with red on the left and blue on the right. So we can calculate a scattering matrix for it. I would like to reuse that for the next time we come across a green layer. Well, here's the next green layer, but now there's a blue on the left and a red on the right. We have to calculate a whole new scattering matrix. Here's another green layer. It has blue on the left, but now green on the right. And we have to calculate it all over again. This is very numerically inefficient if there is a better way. And I can say the same argument about the red and the blue layers. We can step through this and we can see that we've got a lot of work ahead of us. We're going to have to calculate different scattering matrices for each layer, even though very often we're talking about the same layer. So how can we fix this? We're going to go back to how we defined our scattering matrices. We're going to pull a layer out from the stack of layers, and we're going to surround it by free space on both sides. And so now each of the layers, in a sense, will be surrounded by free space. But as long as we make the free space gap between all the layers have 0 thickness, electromagnetically it will have no effect. Okay, we have more to talk about to figure out how to do that. But now let's say we have our 3 unique layers, but they're surrounded by free space. So I can calculate a scattering matrix for this. The fields that it's actually relating exist in free space. The fields in this next layer also exist in free space, so they're compatible. I can connect them, and in fact, I can change all the different orders. So let's envision our stack this way, where I've drawn in these little tiny free space gaps that we will make have 0 thickness. But now let's look at the green layer again. We have a green layer with a red layer on the left, blue layer on the right, but that doesn't matter because we're calculating the scattering matrix here to calculate mode coefficients that exist in this little tiny free space gap and this tiny free space gap. So it doesn't matter what order these happen in. Here we have blue on the left, red on the right, but the fields are still in this free space gap. So here we only have to calculate 3 unique scattering matrices, and we can willy-nilly put these in any order that we want to and reuse them. That is much more numerically efficient, and we can very easily describe some pretty complex structures. The trick is we can't let those free space gaps have any thickness. They will have 0 thickness. So we're just introducing them for mathematical convenience, if you will. So here's our revised geometry. How is it we are enforcing the 0 thickness? And that has to do with how we define our fields on the outside. We have a psi1 and psi2, and we're defining them to exist in the free space regions, but right up against the layer. So they're right at the layer, but in the free space region. And on the other side, our psi sub 2s are in the free space region, but right up against the layer. And so as long as we define all of our scattering matrices with the fields on the outside being right up against the edges of the layer, then when we connect it to the next layer, there is exactly zero thickness between the layers, and then those free space gaps have no electromagnetic effect on your device. If we made those free space layers have some thickness, it could change potentially everything about our device. But we're enforcing 0 thickness. Okay, so how do we calculate our new scattering matrix? Well, we calculate it for the general case, so in fact it's easier for the free space case. And as promised, our layer is now symmetric because it has free space on both sides. So the scattering matrix is symmetric. And we'll notice that S11 and S12 are unique, they're different. But then S21 equals S12, which really means it reflects the same way with a forward wave as it does a backward wave. That makes sense. And S22 equals S11, meaning it reflects the same way no matter which direction we're going. So we only actually have to calculate 2 parameters. So we've doubled our speed. We've made this very versatile because we can change the order of layers however we want to. We're doing fewer calculations, less memory, and our S parameters are consistent with convention. So for all those reasons why I argue the way we're doing scattering matrices in this class, which is different than how anybody else is doing it, is much better. They're much more useful, it's simpler, and more versatile, and that we can change order of all the different layers if we want to. Another thing I'll quickly mention, if we have scattering matrices of lossless layers, so there's no gain and no loss, it turns out our scattering matrices are called unitary. And from a qualitative perspective means it conserves energy. All the energy that goes in has to come out somehow, either reflected or transmitted. Mathematically, there's some other consequences that are sometimes useful. The complex transpose, or the Hermitian transpose, is the same as the inverse of our scattering matrices. So if I take the Hermitian transpose of our scattering matrix, multiply by the scattering matrix, I get the identity matrix. And as we would always expect, if I take our scattering matrix and divide by the scattering matrix, we get the identity matrix. But sometimes that comes up, but this only holds when our scattering matrices are unitary, meaning no loss and no gain. If there is loss and there is gain, these rules do not hold. Another thing I'll mention when you're manipulating equations with these scattering matrix terms, the S11 and S21 are usually the bigger numbers and the more dominant numbers in the matrix. So if you have your choice of which one to divide by, you want to divide by the bigger numbers. So divide by S11 and S22 and your derivations will be much more stable. If you divide by these, while mathematically it's correct, you could end up with a less stable code. In fact, the first time I derived the equations for the scattering matrices, there's many different ways. It sort of worked, but was very noisy. And finally, I figured out I'm dividing by the wrong terms, and that dictated completely how I derived those equations for the scattering matrices. So divide by S11 and S22 if you have a choice, instead of S21 and S12. On to multi-layer structures. So here's the cartoon of our problem. We have a bunch of layers, layer 1, layer 2, 3, 4, 5. So we have 5 layers here. We'll have a wave applied from the left. Some of that reflects and some transmits. We know we're going to calculate a scattering matrix for each of these layers separately. So we have S1, an S1 scattering matrix, 2, 3, 4, and 5. To calculate the scattering matrix of the overall device, we're going to use something called a Redheffer star product. Unfortunately, this is not just matrix multiplication. We can't just multiply one scattering matrix by the next, unfortunately. But we can symbolically write it this way. So we'll star product S1 with 2, 3, 4, and 5, and we'll get an overall scattering matrix, which we are going to call our device scattering matrix. And it'll make sense why we're calling that in a bit. So a big point here is this is what's called a Redheffer star product. It is not a matrix multiplication. Now, since we don't use matrix multiplication to combine scattering matrices, in fact, we never store the scattering matrix as one big matrix. We will store the S11, S12, S21, and S22 as separate matrices and never really ever store it or think about it as one matrix. So here's the Redheffer star product. Symbolically, we write it as some layer A star product with B. So we'll get an overall scattering matrix describing scattering through 2 adjacent layers. So we can write SA this way, we can write SB this way. Our combined scattering matrix has this form, no big deal. If we work through the algebra of this, here are the final expressions for calculating S11, S12, S21, and S22 of the combined scattering matrix. So we're combining 2 adjacent layers here. And in deriving these, I followed all the rules and best practices that we talked about in previous slides. So real quickly, the outline of the derivation is this. We write the definition of the scattering matrix for the first layer. We write the definition of the scattering matrix for the second layer. Now we'll expand both of these into 2 equations and another 2 equations, so we have 4 equations. We will substitute equation 2 into equation 3 and end up with an equation that only has C2 minus. The C2 plus will eliminate. Then we can substitute equation 3 into equation 2 to eliminate the C2 minus and have an equation only with C2 plus. So here are these 2 equations. Now we can substitute our other 2 equations into these 2, and in fact we're left with just a set of equations that have C1 minus, C3 plus, C1 plus, and C3 minus. We eliminated the C2 minus and C2 plus. Those were the intermediate mode coefficients in that between those. So we rearrange terms into this form, and what we're left with are those equations for calculating the Redheffer star product. Not a big deal if you don't follow all this. That's just the derivations for the equations on the last slide. So here's the whole picture. We have our layers surrounded by free space. And we're going to go ahead and we're going to use a Redheffer star product, and we're going to star all these together. And what we're left with, we're going to call our device scattering matrix. And the reason we're calling it that is to differentiate it from something that we'll call the global scattering matrix. So if we connect all the layers of our device together, and we get our device scattering matrix, that is inherently surrounded by free space. And that may or may not be how we wish to model it. If it is how we wish to model it, if it really is surrounded by free space, we're done. Our device scattering matrix is our global scattering matrix. However, if there's ever anything outside the device, we're going to need to connect it to something other than free space. A couple of practical examples of how this could be: if your device is sitting on the earth and you have very, very thick earth underneath, obviously, we need to connect it to that because it is not free space underneath your device. Another time this happens a lot is in optics. We'll design some photonic structure and we'll probably fabricate it on a silica substrate, And that silica substrate is thousands of millions of wavelengths thick, but the structure is maybe a wavelength or two thick. And it's a really good approximation there to approximate what's on the other side of your photonic structure with just an infinite half-space medium. So the point is, we may need to connect it to something on the outside that is not free space. So we're going to come up with two more scattering matrices. We'll have a reflection region scattering matrix, a transmission region scattering matrix, and a reflection region scattering matrix. So our overall global scattering matrix, which describes the final configuration of scattering, has our device scattering matrix, but we star product with the reflection region scattering matrix to connect it to potentially a material on this side, and we star product with the scattering matrix for the transmission region to connect it potentially to something on this side. Now, as I mentioned, if there really is free space on one of the sides, we don't need to star product on that side. But once we've done this and we star product, connect it to whatever's outside our device, the final scattering matrix is our global scattering matrix. So we'll go back to that original definition of our scattering matrices where we had an isolated layer surrounded between two different mediums, and we're going to do this to it. So for the reflection region, we have free space on the right-hand side because that's where our device is, and we need to calculate mode coefficients that exist in free space. But on the left, we want to put in whatever we want. And for the middle, we're free to either put in mu and epsilon or mu naught epsilon naught. That would work. But what we absolutely have to do is make the thickness of that region 0. Otherwise, the modes we would calculate would have extra phase in them, which could change the answer a little bit. So putting this in our original general framework for calculating the scattering parameters, then everything reduces down to this. And we do the same thing for the transmission side. Now we have free space on the left because our device is on the left, and we have mu and epsilon, whatever we want, on the right. And again, we're going to make the thickness of that 0, so it doesn't affect the phase of the transmitted waves. And it turns out the way we calculate this scattering matrix is this set of equations. These look similar, but they're a little bit different. Be careful. There's a minus sign here and a plus sign here, etc. So be careful of the order of the terms here. Okay, making good progress. So I've stepped you through how to calculate this overall global scattering matrix. Now we need to learn how to use that. How do we interpret that to calculate transmitted and reflected power? As a reminder, we have an incoming wave described by a wave vector, k ints, and it has two angles associated with it. It has an elevation angle theta, and it has this azimuthal angle phi, theta and phi. So here's how we calculate our incident wave vector. And also remember from a previous discussion, we have two unit vectors describing our two different polarizations, TE and TM, and we calculate them with this recipe. Once we have these two unit vectors, our overall composite polarization vector is the amplitude of our TE wave times the unit vector of the TE wave, plus the amplitude of the TM wave times the unit vector of the TM mode. What we want to choose this in the end so that its magnitude is 1. That'll be very useful to us. Not absolutely necessary, but it's going to make our transmission and reflection calculations much easier. Okay, onward. So we have a global scattering matrix, and it relates inputs to outputs. So let's look at this picture on the lower right. I've never actually modeled anything with an input coming from the right. There's usually only one wave hitting your device. If there is two, you'd have to keep that. But 99.99% of the time, you're not going to have a second applied wave. So we'll drop this, and we don't typically use it. So that would come in here. But we only have one applied wave. We'll just call the mode coefficients of that C incident. If we multiply this by the global scattering matrix, we get the mode coefficients of the reflected modes and the coefficients of the transmitted modes. So how do we get C ints? It's our it's the x and y components of our applied wave, and then we are pre-dividing by the eigenvector matrix in the reflection region to get the mode coefficients. And remember that the x and y components of the applied wave really are those two polarization vector components that we calculated on the previous slide. So we'll calculate px and py, and that's px and py here. This is always going to be the identity matrix. So in fact, the mode coefficients of the incident wave really just are px and py. I mentioned we never really use the scattering matrix as an overall matrix, and we're going to store the individual components separately. So in fact, we're going to be using these two equations to calculate mode coefficients of the reflected waves and mode coefficients of the transmitted waves. Reflected waves is just S11 times the applied wave. The transmitted wave is S21 times the applied wave. So now we have taken our global scattering matrix and calculated the mode coefficients of the reflected and transmitted waves. We still don't know how much power is in them relative to the applied power. Right now we just know the mode coefficients. In order to calculate power, we need to calculate what the electric fields are. So remember how these are related. The electric fields are the eigenvectors times the mode coefficients. Now for our case, remember this is the identity matrix, so in fact our mode coefficients are the field components. But when we get to higher order models like rigorous coupled wave analysis method lines, that won't be the case. So let's leave the W in there. Cref was S11 times the applied mode coefficients, and the applied mode coefficients were the inverse of the reflection eigenvectors times the fields. And remember, these were the polarization vectors. And we could step you through the same thing for the transmitted side. So at this point, we'll know all of the tangential components, Ex and Ey. We need the Z components. And so we'll get that from the divergence equation. The divergence equation sets a rule relating the X and Y components of E. So if we know two of them, we can calculate the third because they have to satisfy divergence. So we go through all this and we can calculate the Z component this way. Now the X and Y components are the same throughout all the layers, but the Z components change, so we need different Z components depending whether we're calculating power in the reflection region or the transmission region. So we'll have two of those now. Once we know all three field components, now we can calculate how much power is in those waves. And usually what is more interesting or more useful, instead of how much power is in the transmitted reflected wave, it's what fraction of power are in the reflected and transmitted waves. So how much of the power from the applied wave ends up being reflected or transmitted. And we'll call that reflectance and transmittance, defined as the fraction of power that's either reflected or transmitted. So here's how we'll define it. Power in the reflected wave is proportional to the electric field squared. Power in the applied wave is proportional to the electric field squared. But we can calculate reflectance as just the ratio of those two, because whatever constants might be out here to calculate the actual power would cancel. So we calculate reflectance this way. In lecture 7, we're going to step through this derivation in detail. We're going to skip it right now. Suffice to say that we calculate our transmittance this way. So this will be the fraction of power from the applied wave that ends up being transmitted. So we have a similar ratio here of the amplitude squared of the transmitted wave divided by the amplitude of the applied wave. But we have the real part of the ratio of the permeabilities, the relative permeabilities, and the ratio of these K vectors. So it's a little bit strange that they're there, and we'll get into that in lecture 7. Now once we know reflectance and transmittance, it is always a good idea to check for conservation of energy. So if we add reflectance and transmittance, assuming we didn't have any loss or gain in our model, the sum of those should equal 1. Now if we put loss in our model, that should come out being less than 1. And if we put gain in our model, it comes out to be greater than 1. And if we have loss and gain, who knows what it'll be. But even if you're going to model loss or gain, It's always a good check. Build your device. Turn off the loss and gain at first. Model the device without the loss and gain. Make sure that conservation of energy is held, because if it's not, clearly something's wrong with your code. And if you had just immediately put in the loss or gain, it's hard to say whether there's a problem with your code or that is the correct answer. So check for conservation of energy, then turn on the loss or gain, and you'll have a higher degree of confidence in your answer. It's still not a guarantee that it's right, but it's definitely wrong if you violate conservation of energy with loss or gain turned off. So let's add a couple of notes and hints about implementing this method. So storing the problem, there's no grid here. We just store all the information for the layers separately. So what is the information for all these different layers? Well, I like to store the relative permittivity in a one-dimensional array. So here we're talking about 3 layers that'll have a dielectric constant 2.5 in the first layer, dielectric constant 3.5 in the second layer, and a dielectric constant of 2.2 or 2.0 in the third layer. Then I'll store the relative permeabilities in a same 1D array, and then the layer thicknesses in yet another 1D array. So this describes our layers. Well, we also need the materials in the external regions. So ER1 and UR1 are so ER1, UR1 is the relative permittivity and relative permeability on the reflection side of the device. And then ER2 and UR2 are the relative permittivity and relative permeability on the transmission side. We need the angles of the source, theta and phi. We need the amplitudes of our 2 polarizations and wavelength. So this set of information will completely describe the problem. We'll put that at the front of the code, and then the rest of the code will all be relative to this. And I mentioned this before, but we never use the scattering matrix as just one big matrix. We're always using the 4 individual terms, S11, S12, S21, and S22, individually. So we store them individually. We never store it as one big matrix. Let's talk about an efficient star product. This isn't such a big deal for transfer matrix method, but the size of the matrices, of these scattering matrices, is going to grow a lot when we get to higher order methods like rigorous coupled wave analysis and method of lines. So this scattering matrix calculation, as simple as it looks, is actually going to be pretty time consuming. And right away we can see some redundant calculations. Notice this inverse term here is the same as the inverse term here. This inverse term is the same as this inverse term. So we don't want to do that twice. So I like to calculate these ahead of time, and then we calculate the 4 terms of the combined scattering matrix this way. So it saves some redundant calculations, and it's a bit faster. So I like to do it that way. It's not necessary, I just think it's a little bit faster. Let's talk about some simplifications that are specific to the transfer matrix method, which is a one-dimensional model, and it's also specific to linear homogeneous isotropic media. So all the eigenvector matrices for the electric fields are just the identity matrix. Our omega is always reduced down to just j kz times I. This means that our eigenvalue matrices are just omega. We mentioned that before. Since omega is a diagonal matrix, that's what made the eigenvector matrix the identity matrix, and the eigenvalue is simply equal to omega. So here is our original equation for calculating the eigenvectors of the magnetic fields. Well, W is the identity matrix, so it drops out. And in fact, we don't need a lambda matrix because omega is that. So we can calculate V as just Q divided by omega. For calculating our A and B constants, when we're doing star products and calculating scattering matrices, if these are both the identity matrix, then this product or division will be the identity matrix. So in fact, we can use these equations now to calculate A and B. The mode coefficients of the applied wave are just the 2 x and y components of the polarization vector, and the electric field components of the reflected waves is just S11 times those mode coefficients we just calculated, and the same thing for the transmitted side. So because our W's are the identity matrix. So a lot of these equations simplify down even further. I like to set up my code, and there's a block diagram on the next slide, but I set up a loop that will iterate through all of the layers. It'll calculate the scattering matrix for the first layer and update a global scattering matrix. It'll go to the second layer, and it'll calculate the scattering matrix of the second layer and update the global scattering matrix. And it goes that way. So in order to make that loop sort of dumb, we have to initialize a global scattering matrix before entering into that loop. And we need this global scattering matrix before it enters the loop to be what I'll call a nothing scattering matrix. So if it is a nothing scattering matrix, I know right away it's going to have to transmit 100 of the power and not change any of the phase. So in order to do that, the S12 and S21, which are the transmission scattering parameters, we'll just set to the identity matrix. So 100% of the power goes through and no phase change. And it can't reflect. A nothing scattering matrix can't reflect. So S11 and S22 will set to the zero matrix. So our overall global scattering matrix looks like this. Now that is not the identity matrix. This is where a lot of people trip up. If this were the identity matrix, you would have two i's going on this diagonal and zeros going along this diagonal. So we can't initialize this as the identity matrix. And we shouldn't be doing that anyway, because we never treat the scattering matrix as one big matrix. We'll always treat the four elements of it individually. Okay, so here is the block diagram. This is the part that hopefully will bring peace and harmony. We have equations flying all over the place, and this is where we all come together and we talk about what happens first, second, third, fourth. So we start our algorithm. The first thing I like to do is calculate the wave vector components. Remember, these are normalized, so there's no k-naught. There, in principle, should be a k-naught here, but they drop when we normalize. So it's just the refractive index of the incident region times sine theta cosine phi for the x component, and refractive index times sine theta sine phi for the y component. Next, we need to calculate the parameters for free space. Remember, we're surrounding all of our layers by free space, so we'll need these to calculate our scattering matrices. So the z component in free space is the square root of 1 minus kx squared minus ky squared. We have our q matrix. We calculate our v. Those are the eigenvectors of the magnetic fields. Notice we don't need w, because that will always be the identity matrix here. And we can calculate omega. And we won't need our lambda matrix either, because that is just omega for this special case. When we get to higher order methods, that won't be the case anymore. Before we enter our main loop, we initialize our global scattering matrix. And while I'm writing it this way, really we're setting S11 to 0, S12 to the identity matrix, S21 to the identity matrix, and S22 to 0. Now we're ready to enter the main loop. So we come into the first loop. We're talking about the first layer. We'll calculate the kz component in that layer. We'll calculate the q matrix in that layer. We'll calculate the omega matrix in that layer and the v matrix in that layer. So these are all parameters associated with, at this point, the first layer. Then we calculate the scattering matrix for the first layer. So these equations shouldn't be any surprise. Once we know that, and we have this nothing global scattering matrix, we can do a Redheffer star product to update the global scattering matrix. So we'll take our previous global scattering matrix, and right now it's this, and star product it with the scattering matrix for the first layer that we just calculated. And that will become our new global scattering matrix. Now we go back to the loop to the second layer, calculate the parameters for the second layer, calculate the scattering matrix for the second layer. Now we come in and we take our global scattering matrix now, which only has layer 1 in it, star product with the scattering matrix for the second layer, and now our global scattering matrix describes layers 1 and 2. And then we go through and do layer 3 and 4 and 5 and however many layers we have. And finally, when we're done, we come out with this global scattering matrix, which at this point is actually the device scattering matrix. So at this point, it's connected to free space. Well, so now we need to calculate the scattering matrices for the reflection and transmission regions and connect it. So now we have the true global scattering matrix. Then we calculate our source, so we're going to have to calculate the unit vectors in the TE and TM directions following the recipe that we had. Calculate this composite polarization vector, maybe even add an extra line of code to enforce that its magnitude is 1. Now we know the mode coefficients of the incident wave. So now we can calculate the reflected and transmitted fields using S11 and S21 of the global scattering matrix. These are just the transverse components. We calculate the longitudinal components in the reflection and transmission regions. Then finally we can calculate transmittance and reflectance. And while I'm not showing it here, a really good final step is to check for conservation. So that's it. That is the transfer matrix method. We'll end this lecture with a quick discussion on some advanced scattering matrices stuff that will help you describe much more complex devices. First, let's talk about longitudinally periodic devices. So what do I mean by that? Let's say we have 3 layers, red, green, and blue, and we're calling them A, B, and C. And then let's say those 3 layers repeat. So red, green, blue, red, green, blue, red, green, blue. Well, we can calculate the scattering matrix for one unit cell. That's just SA star SB star SC. So this composite scattering matrix describes 3 layers. So how can we efficiently describe propagation through this stack of 8 unit cells? Well, one way we can do it is just say SA star SB star SC star SA star SB through all of these layers. That absolutely will work, but that's the least efficient. One thing that's a little bit more efficient, but still inefficient, is to take the composite scattering matrix and star product it with itself 8 different times. Well, this is 3 times faster, 3 times as efficient, and we still get this overall scattering matrix. But it turns out there's a better way to do this. And we'll call it cascading and doubling. So the first step is to calculate the composite scattering matrix of what we'll call a unit cell. This is the stack of layers that repeat themselves. And so we'll call that S times 1. And the times 1 means that's how many unit cells our scattering matrix is describing. So it's SA star SB star SC. Well, now we can take the scattering matrix describing one unit cell and star product it with itself, and we get a scattering matrix that describes 2 unit cells, or actually 6 individual layers. Well, now we can take this matrix and star product it with itself, and now we have a scattering matrix that describes 4 unit cells, or 12 layers. We can take this scattering matrix that describes 4 unit cells, star product it with itself, and now we have a scattering matrix that describes 8 unit cells. And so this process will repeat. We double each time, 16, 32, 64, 128, 256, and very, very quickly we can describe a huge, huge number of layers. It's very easy to do thousands and even millions of layers doing this. Fiber Bragg gratings is an area where this comes in and you'd want to do something like this. But there's one problem with that algorithm. What if the number of layers you want is not some power of 2? Suppose we want 17 unit cells or 26, and it's not a multiple of 2. So we can generalize this a little bit, and here's how you do it. So the first step is to calculate the scattering matrix of the unit cell. This is the thing that you want to cascade and double, so it's still SA, SB, SC. Then what we'll do is we'll take how many layers that we want to repeat, and let's say that's 10. We want 10 layers. That's not a power of 2. 8 and 16 are the powers of 2. We're going to convert this to binary, 1, 0, 1, 0. And so the way this will happen, we'll initialize our algorithm, our global or maybe device scattering matrix, I should have called it. We'll initialize it this way. And we will construct a scattering matrix for just one unit cell. And we will initialize our cascaded and doubled scattering matrix with this. So right now, while that's n layers, it's only going to be 1. That's just how we initialize it. Then we go into the algorithm. Well, we look at our first binary digit. If that is a 1, then we need to include this scattering matrix into the global scattering matrix. If it's not, we just go on. And so right now we have a binary digit of 0. We don't need it. But what we will do then is do a cascading and doubling step. We're going to update this S times N by star producting with itself. Well, if this is our first pass through the loop, this is now going to describe 2 unit cells. Well, now we go back. Let's look at the second binary digit. That is a 1. So in other words, we need S times 2, or the scattering matrix that describes 2 unit cells. So we're going to update our global scattering matrix by star producting it with whatever this cascaded and doubled scattering matrix is. Then we go ahead and we double it again. And this will now be describing 4 unit cells. And we go back. Is that place a 0 or a 1? It's a 0. We don't need that one. But we will go ahead and double again. And now we're describing 8 unit cells. And we go up. We do have a 1. So we update our global scattering matrix then with the times 8 scattering matrix. And we're done. We've gone through all the binary digits. Our global scattering matrix is essentially going to be S8 star producting with S2. So 8 unit cells and 2 unit cells gives us 10 unit cells. Dispersion analysis. This is not something we're going to investigate in this course, but I'll throw it out to show you what it is. So we will construct a scattering matrix of just 1 unit cell. And there may be n layers in here, so I just put in Sn, because your unit cells might be hundreds of layers, who knows. We're going to rearrange the terms almost into the form of a transfer matrix. Remember, scattering matrices related inputs to outputs. Transfer matrices relates mode coefficients on one side to mode coefficients on the other. So we took our scattering matrix equations, separated into 2 separate equations, moved terms left and right, and then brought it back together. So what we have are the mode coefficients on the left to the mode coefficients on the right. So now we're going to apply a periodic boundary condition. If this is a periodic structure, then the modes on the right have to be the same as the modes on the left, or the input side, but with phase added to them. So we have a periodic boundary condition, if you will. So now, rather than write this as CNs, we can add in the phase here, and we have a new matrix equation. Well, it turns out this is an eigenvalue problem, and we can solve it, and we can calculate all possible solutions of k sub z, and that'll tell us how these waves are moving through this periodic material. We know at a microscopic level all the waves are bouncing around, but if we sort of squint our eyes and blur it and look back, we see an overall wave envelope that travels through this stack of layers, potentially slower than we would expect, and we can calculate that through this dispersion analysis. And lastly, I just want to throw out some alternatives to scattering matrices. I really haven't coded many of these, so all I can do is point to them that they exist and tell you what the claims are in the literature. So of course there's transfer matrices, or a different flavor of this is the transmittance matrices, and there's even a technique called the enhanced transmittance matrix method, which is very fast, about 10 times faster than scattering matrices, and it is stable, but it's not memory efficient. It's one where you have to work backward through the layers, storing a bunch of parameters for each layer and then working forward, and you can run out of memory. It also isn't able to do cascading and doubling to exploit the periodicity. It was the first method, but it's essentially been replaced by scattering matrix now, so it's not as popular in the literature. Well, if we go back to network theory from circuit analysis or microwave class, we know there's a bunch of different matrices that we can use to wrap black boxes around circuits. And there's these hybrid matrices, which are essentially relating current and voltage through this equation. It's relating current and voltage on either side of the port. So we can describe our fields in terms of these H matrices. Supposedly it's a bit more stable than scattering matrices. I'm not sure I believe that one. They say it's a more concise formulation, maybe. They say it's simpler to implement, maybe. I don't know. They say it's about 30% better than the enhanced transmittance matrix method. That's hard to believe because that's a pretty fast algorithm. And it is unconditionally stable. I believe that one. And all of these may be true. I just don't have any experience to draw from to confirm that. And another one you may see is R matrices, which relates currents to voltages. And also argued to be unconditionally stable with improved numerical efficiency. I do believe it's stable. The jury's out on the numerical efficiency. I'd have to try it myself to really say, yep, it's better. So that's it for the transfer matrix method based on scattering matrices.